This is the unit circle. So I have 0 here at 0.7 E, J, 0.7 pi. And then another 0 here, that's E, J, 0.9 pi, almost pi. And then I have another 2 zeros here. One is E, negative J, 0.9 pi, and E, negative J, 0.7 pi. So this is the information that you were given. And based on that, you created the difference equation of this system or of this filter. Questions? Look at this example. So we have electromagnetic interference from the power lines that causes 50 or 60 hertz noise to a ECG signal. So the signal that we are expecting should be like a very clean signal with no noise. But because we are working in an area where there is some electromagnetic interference comes from power lines. So that make the signal looks like this. And you can see there is a noise here. And we know that the power lines has a range of frequencies 50 to 60 hertz. So our goal is to design filter, notch filter. That means that it will filter out specific frequencies. Let's say that we design to reject 50 hertz noise on the signal, if the signal sampled at 500 hertz. Sampling frequency, that's 500 sample per second. So we can find what is the sampling interval. Sampling interval, which is T, should be 1 over sampling frequency. That's 1 over 500 second per sample. Seconds per sample. So we are trying to remove or to clean out this noise from our ECG signal. So at sampling rate of 500 hertz, the frequency 50 hertz corresponds to a discrete frequency of, we use the relation between the digital frequency and analog frequency, capital omega equal omega times T, right? So this frequency in hertz as in radians equal 2 pi 50 radians per second. All right, so if I want to convert that to discrete frequency, 2 pi 50, that's omega, times the sampling interval, which is 1 over 500. So the unit of this one is radians per second, and the unit of the interval is second per sample. So that's 100, and we have 500 down there. That's pi over 5. And the unit will be radians per sample. So this is the frequency we want to eliminate with our discrete time filter. That means we need to design filter that has zeros at z equal what?
To the j plus or minus pi over 5.
Exactly, pi over 5. We want to design a filter that rejects specific frequencies. So again, we find the transfer function of the system that has these two zeros. So that will be 1 minus E j pi over 5 z negative 1 time before DC gain correction. Just 1, right? So that will be 1 minus 1.618 plus 1. That give you 0.382. So we need to divide by this number. That's about 2.62. If you don't understand why we did this, please ask. Question about that? Why we wanted to ensure a unity gain at DC?
Is it so that we don't like increase the like magnitude of the output signal so it's not greater?
Yes, we want to keep it as it was originally. So this is the signal. It has here, it was like at 0.6. This is the original one. This is the filtered one.